welcome to the APECE Chapter 12 Gaseous Chemical Equilibrium Problem Set with me, Mr. Wilkosz. Let's look at Problem 3. In Problem 3, you are given some information in a more complete table than what's pictured here on this first slide that all describe a reaction 3A that's in a gaseous state plus 2B, also in a gaseous state, in equilibrium with C with a coefficient of 1, also in the gaseous state. You're given information at time 0 that the pressure of A is a certain number of atmospheres, the pressure of B is a certain number of atmospheres, and the pressure of C is non-existent yet. So by Le Chatelier's principle, you know this equilibrium is going to shift to the right to give more of C. You can figure out exactly how much by making an ice box or an ice table, and it's in atmospheres for this particular problem. You know that since you have no product C, that the equilibrium is going to have to shift to the right, and so you can safely assume that the A will decrease by a quantity of 3 times whatever the amount that C increases by, and B will decrease by an amount that's 2 times the amount that C will increase by. And since you know the concentration of A in the end, you can write out an algebraic equation, 2.450 minus 3x equals 2.000, and that's in atmospheres. You can solve for x as 0.1500 atmospheres, and then plug it back into the other equations. 1.50 minus 2 times 0.1500 will get you the pressure that B will be. And then 0 plus 0.150 will get you the pressure that C will be. So the end result of that is 1.20 and 0.1500 as the pressure after 10 seconds. When you head to the second set of scenario, time-wise, you're getting to 20 seconds, and you repeat the same sort of process. You set up an ice box, and I set it up so that we're headed from 0 seconds to 20 seconds, so I'm totally skipping over 10 seconds, but I'm starting at 0 seconds and moving to 20 seconds. But I set up equations in the same sort of way, where I was able to write an equation and know that C will increase, because at 0 seconds there is no C, so it has to increase, and I'm able to figure out what X is. X has to be 0.275 atmospheres, and then you can just kind of do a little bit of math. 1.50 minus 2 times X and 2.450 minus 3X get you the end results here of what you should have for 20 seconds. For part quote 3 of this number 3, I went from 0 to 30 seconds. They tell you what the pressure of B is, and I just sort of shortcutted the algebra here, and I was able to find out that X is 0.35 atmospheres. And when X is 0.375 atmospheres, when X is 0.375 atmospheres, you know that this is going to fill out to be 0.375. And you can work through the math to find out that the pressure of A will be 1.325. Looks like those predictions were right. Same thing with 0 to 40 seconds. You can solve out using the equation for pressure of A and find out that X is 0.450. If you solve that out, you'll get the pressure of B to be 0.6 and the pressure of C to be 0.450. For 50 and 60 seconds, you actually start to reach, this thing begins to reach equilibrium. As it proceeds towards equilibrium, you can't tell exactly when it gets there until you calculate it out. So to get from 0 to 50 seconds, you can actually figure out what the pressure of the substances will be. You use the equation C because you're given how much pressure is present for C at 50 seconds. It's been measured as 0.50 atmospheres. So you can find out that X is 0.50. Then you can find out that pressure of B must be 0.50. If you do some subtraction, the pressure of A drops from its original amount of 2.450 to 0.950. Now what you notice here is that the pressure of the 50 seconds pressure A and 60 seconds pressure A is the same, so this thing has reached equilibrium under these conditions.